to yet another thesis defense. It's my pleasure to introduce Tao Yu. I think he does not need any introduction with this crowd, but I should say that it was my pleasure to work closely with him. He started his master's with under Judy's supervision, which culminated with the first generation of devices. He overcame disappointments and picked up on the encouragement that such devices were presenting, and then did a spectacular job with his second set of devices, about which he's going to be talking about today. So he started with Judy, and I was his co-supervisor. Now he's finishing under my supervision with Judy as co-supervisor. But Judy was the primary architect behind the technology from the beginning, so that's a tribute to her contribution. So without any further ado, let me get this going, and Tao, it's yours.
Okay, thank you so much for the introduction. Good afternoon. Thank you for coming to my thesis defense. The title of my thesis is Indium Gallium Arsenide, and Timonite Quantum Well Tunnel-FET for Ultra-Low Power Applications. My advisors are Professor Judy Hoyt and Professor Dimitri Antoniadis, and the committee members are Professor Jesus de Alamo and Professor Ronan Han. So this is the outline of my presentation. Firstly, I'll go through some motivation and background, and then I'll introduce the design and fabrication technology of InGaAs gas quantum well TFETs. And then I'll present the characterization results of the quantum well TFETs before I go into detailed analysis of gate efficiency and intrinsic tunneling steepness of the devices. In the fifth part, I'll focus on the non-logic applications of devices before I conclude. So in the first place, why do we care about TFETs? So for the past decades, we have witnessed the technology boom, making all these various applications available to the markets, like smartphones, smartwatches, medical implants. As you might have noticed, that these applications are all powered by either battery or energy harvesting devices that can only provide a very limited amount of power. So the successfulness of these applications really relies on the power efficiency of their components, especially the integrated circuits like CPU or GPU. So all we care about is the power consumption of the integrated circuits. Unfortunately, we have seen that the power density of the integrated circuits are growing rapidly with the technology node, especially the substrate power, which is the power consumption when all the transistors are turned off. And this will become a disaster if we can't reduce the power consumption of the integrated circuits. So what can we do about it? If we take a look at the equation of the power consumption of single transistor, we can see that the power consumption of the transistor can be reduced by reducing either both the power supply voltage VDD and current leakage. So as a matter of fact, the power supply voltage scaling was carried out at the early ages until the 19 nanometer technology node. The slowing down of the power supply voltage scaling is because the exponential increase of the off-current leakage. So in here, I'm plotting three transfer characteristics of a normal MOSFET at different power supply voltage. As you can see, the off-current leakage increased exponentially when we decrease the power supply voltage linearly. And this gives rise to the exponential increase in the power in the substrate power. And this is due to the 60 millivolt per decade substrate swing as shown here when we try to maintain the performance of the transistor, that is the on current of the transistor. So where does that physical limit of 60 millivolt per decade substrate swing at room temperature come from? So this is the band diagram of a normal MOSFET, and when we try to modulate the conduction band of the channel with the gates, it's sweeping this 60 millivolt per decade thermal tail which is a result of the product of Fermi distribution and the density of states. So that the inversion charge density can only increase by 1 decade with 60 millivolt of gate bias. So because of this 60 millivolt per decade physical limit of substrate swing in MOSFET, we can't really achieve lower power supply voltage unless we introduce steep slope devices which can potentially provide both on and off currents with smaller voltage window by using alternative physics. And this is where T-FET come into play. So this is the design of the T-FET, which is very similar to the MOSFET except for reversely doped source and drain. And with the help of the band diagram on the right, we can see that there's no current flowing when we apply zero gate bias. And then the band-to-band tunneling can happen from the valence band of the source into the conduction band of the channel when we apply sufficiently large gate bias. And why does this doesn't have 60 millivolt per decade physical limit? Is because when we try to modulate the conduction band of the channel, the band-to-band tunneling doesn't need to sweep through this thermal tail. And in fact, if these band edges are infinitely sharp, the substrate swing of the T-FET should be infinite because there's no current before the bands are aligned. Besides this lateral design of the T-FET, it can be also designed vertically, and this is the inline T-FET. The difference between the inline T-FET and the lateral T-FET is that the tunneling direction of the electrons are aligned to the gate electric field. So because of this design, the gate modulation can be uniform across the entire tunneling junction to promote the current density. So I will focus only on this device structure due to its superiority than the lateral T-FET. In addition, if we make the channel layer thin enough to form a 2D electron quantum well and use different material for the source, this device structure becomes heterostructure quantum well T-FET, which is the subject of my thesis. So the concept of T-FET is brilliant because it can overcome the 60 millivolt per decade physical limit, and it has been proved with various simulation studies as shown in the figure on the left. So there are tons of solid lines that are different simulation results, and they are most of them are superior than the 16 nanometer FinFET CMOS technology in both substrate swing and on current, which are preferred in digital application. However, the experimental results are quite disappointing as seen from the right. And all these solid lines, most of them are below the 16 nanometer FinFET technology, meaning that they have very low drive current. And even for those with relatively high drive current, they have almost no switching characteristics. So where does this huge discrepancy come from? They are from the non-idealities in the T-FETs that are not included in the simulations. So here I'm going to introduce 3 different non-idealities in T-FETs, and one of the most significant one is the parasitic thermal currents. So these currents are thermally activated, and then they are in parallel with the tunneling current. So if they're large in scale, especially in the substratial regime, all we measured is the substratial swing of these thermal currents, which is no steeper than 60 millivolt per decade at room temperature. And there are different mechanisms of these thermal currents. And here is the band diagram of an inline T-FET in the direction of electron tunneling. So here I'm showing the direct recombination at the tunneling interface. And this is the SRH recombination with the recombination center. And the third thermal current mechanism is called the tunneling assisted generation, consisting of a tunneling process from the valence band of the source into the unoccupied interface trap state, and then get thermally emitted into the conduction band of the channel. So some of these mechanisms have gate bias dependence, some don't. But with the presence of the thermal current, as you can see in here, the measured substrate swing is difficult to go below 60 millivolt per decade, even if the band-to-band tunneling provides a much steeper substrate swing. In addition, these thermal currents have a very strong temperature dependence. So as shown in this work presented on IEDM 2012, the substratial behavior changed a lot when the temperature dropped from 300 K down to 77. And this indicates that the substratial regime are pretty much dominated by thermal currents. A more recent development on the InGaAs Tunnel-FET shown on IEDM 2013 have almost no temperature dependence in the substrate behavior, which implies that the thermal currents in this device has been successfully mitigated. The second non-ideality has to do with the non-abruptness of the band edges. So theoretically speaking, the band edges of the conduction band and valence band should be infinitely steep, meaning that there's no density of states beyond these edges into the band gap. So the band-to-band tunneling shouldn't happen before the conduction band of the channel and the valence band of the source start to align. However, this is not the case in reality. In fact, Urbach has discovered over 50 years ago that there is an exponentially decaying density of states into the band gap as shown here in the dashed line. So because of this band tail, the band-to-band tunneling can happen even before the bands to start to align through these density of states in the band gap. And this tail is even heavier when we dope the material with the doping concentration over 10 to the 18 per cube centimeter. So this band tail gives rise to the finite steepness of the substratial swing in the TFETs. The third non-ideality is the gate efficiency, which is the inefficient gate modulation in any MOS structure, including MOSFET. So the definition of the gate efficiency is already established, which is the modulation of the surface potential divided by the modulation of the gate. So this quantity is actually pretty mysterious because we can't really probe or measure directly. And it has to be extracted either using a modeling or simulation. So with all different kinds of non-idealities in TFETs, the measured substrate swing can be approximately written as the product of three terms. The first term has to do with the rivalry between the tunneling current and the thermal current, whichever is larger. And then the second term is the gate efficiency as I just introduced. And the third term is the gate efficiency degradation due to the presence of interface traps. Among all these four variables, the intrinsic tunneling stiffness and the gate efficiency are intrinsically related to the design of the TFET, while the other two terms are coming from the fabrication process. So we want to understand the intrinsic tunneling property of the TFET, but with all these variables, we can't really get anything. So fortunately, we can eliminate or suppress the thermal current and the interface traps at low temperature, leaving these two intrinsic terms. But they can't be separated with temperature dependent measurement because they don't have temperature dependence. So the gate efficiency has to be quantitatively extracted either from modeling or simulation. So the goal of this study is to first design and fabricate the quantum well TFET with InGaAs gas heterostructure. And then I want to study the gate efficiency in TFETs and understand the bottleneck of the TFET substrate swing due to gate efficiency. With the knowledge of gate efficiency, I want to investigate the intrinsic tunneling steepness of the heterojunction and then relate it to the non-abruptness of the band edges. After that, I want to optimize the gate efficiency in quantum well TFETs using simulation. And lastly, I want to explore the non-logic TFET application given the current unoptimized device performance. So next, I'm going to introduce the design and fabrication technology of InGaAs gas quantum well TFETs. Here is the 3D schematic view of the device. This is the InGaAs on gallium arsenide and timonite heterostructure with the effective band gap at the tunneling interface of 400 millielectron volt, including the quantum mechanical effect. So with this effective band gap, the carrier recombination as introduced earlier, including direct and SRH, can be significantly reduced. And then there is an extremely thin indium phosphide cap below 1 nanometer between the hafnium oxide gate dielectric and the InGaAs channel. So with this indium phosphide cap, the density of interface traps can be reduced, and the tunneling assist generation, as I introduced earlier, can be suppressed due to the 200 milli-electron volt extra conduction band offset from the indium phosphide. Lastly, the device includes a self-aligned air bridge structure and the self-aligned source recess to eliminate any of these two kinds of parasitic tunneling paths without gate control. So here is the cross-sectional view of the device. And this is the epitaxial structure of the starting substrate. So the key design parameters are shown here. The distance between the gate and source is 500 nanometers, and the gate is self-aligned to the drain, leaving LGD of 25 nanometers. And the thicknesses of the gate dielectric, InGaAs channel, and the source are 4 nanometers, 15 nanometers, and 153 nanometers respectively. And here I'm showing the doping concentration of the channel and the source. Here I'm going to show you the fabrication process. With the starting substrate, we first deposit the molybdenum contact layer and the Thai gold hard mask. And then the molybdenum layer was reset with dry edge, and the heavily doped InGaAs contact layer was reset with wet edge, achieving this 25 nanometer undercut. And then the indium phosphide cap was reset to sub 1 nanometer using precisely controlled digital etch before I deposit the hafnium oxide using ALD. And then the gate, the platinum gate was deposited self-aligned to the drain. After that, the channel layer was reset self-aligned to the source and to the gate and drain. And then the nickel platinum gold source contact was deposited. The next step is the most critical step, which is the air bridge formation and then the aluminum oxide passivation layer deposition. The last step is the back end of line process, including an interlayer dielectric deposition via hole opening and the pad placement. So this completes the device fabrication. Here are some SEM and TEM images of the fabricated device. As you can see here, the air bridges are completely suspended using highly selective wet edge undercutting the gadolinium antimonide layer. As you can see from the TEM image, the gate is self-aligned to the drain, leaving 25 nanometer gap between them. And this is the high resolution TEM of the gate stack. The hafnium oxide and indium phosphide cap thicknesses are 4.4 and 0.58 nanometers respectively. So with the successful fabrication of the device, I'm going to present the characterization results of the devices. Here are the room temperature transfer and output characteristics of a typical TFET with minimum substrate swing of 87 millivolt per decade. So although this number is not as good as sub 60, but I'll explain later that the tunneling current steepness is actually sub 60. And from the transfer characteristic, the drain-induced tunneling barrier lowering, which is the separation between the transfer curves at different VDS, is very small, especially a high VDS. This indicates excellent gate modulation, and it can also be seen from the saturation current from the output characteristic with high VDS. From log scale output characteristics, the gate bias dependent negative differential resistance was observed, which is an evidence of the band-to-band tunneling process. The transfer characteristics of the device was measured from 77 Kelvin to 300 Kelvin at low VDS, which is shown here. As we can see, that both substrate swing and the off-current leakage are improving at lower temperature until 140 Kelvin. So as a matter of fact, these four curves below 140 Kelvin are almost the same except for the threshold voltage. It can be clearer in the substrate swing versus drive current curves, as shown in the middle, that these four curves are almost overlapping with each other. And this indicates that the substrate swing below 140 Kelvin are temperature independent. So it is the product of the intrinsic tunneling steepness and the gate efficiency. In fact, this is not the only device behaving like this. And in this minimum substrate swing versus temperature plot, we have 4 devices from different batches. Although they have different behavior at higher temperature, they all behave the same below 140 Kelvin. The multi-frequency split CV characteristics of the TFET was also measured, and the room temperature CV characteristics shows certain frequency dispersion, which means that there's interface traps that degrades the gate modulation of the device. And the low temperature CV characteristics has no frequency dispersion, meaning that these interface traps are deactivated at low temperature, which is consistent with what we observed previously of the temperature-independent substrate swing. So as a summary, we have successfully fabricated the InGaAs gas quantum mode TFET with a room temperature substrate swing of 87 millivolts per decade, and we observed a very low DITL and good saturation with high VDS, as well as the gate bias-dependent NDR at negative VDS. With the temperature-dependent measurements, we observed the temperature-independent substrate swing below 140 Kelvin, which indicates the elimination of the thermal components from the device drive current and deactivation of the interface traps at low temperature. So the achieved tunneling current steepness is 50 millivolts per decade, which is the result of the product of intrinsic tunneling stiffness and the gate efficiency. Still, neither of these quantities are known. So I'm going to talk in detail about how to extract these 2 quantities from modeling and simulation. Before I go into detailed extraction scheme, let me first talk about the definition of gate efficiency for both modeling and simulation. From behavioral point of view, the TFET can be modeled as a tunneling diode in series with a MOSFET. So the definition of gate efficiency for this model can be written as the incremental voltage across the tunneling diode divided by the incremental voltage at the gates. As for simulation, the physical definition of gate efficiency, which is the incremental surface potential divided by the incremental gate potential, can be extracted directly. However, if we think about the model I just presented, and this is not exactly the same as how the quantum mod TFET behaves. So if we revise the model based on the behavior of the quantum mod TFET, it can be modeled as the distributed network shown here. In here, what is missing in the previous model are the series resistance induced from the quantum wells and the source and drain. So for simplicity, we use a lumped model as shown here, but we take into account the series resistance from the quantum well and the source and drain contacts to truly reflect the behavior of the quantum mod TFET. As for the detailed model, MIT virtual source model was used for the MOSFET, and Keynes model was used for the tunneling diode. Here I'm showing the complete equivalent circuit of the quantum mod TFET, and this part is the tunneling diode, or is the junction capacitance and the variable tunneling resistance. And this part is the MOSFET from the virtual source model. And here are the gate parasitics and drain parasitics from the pads and the wires. So this model was implemented in Verilog A thanks to Ujjwal, and it can be used for both DC, AC, and RF circuit simulations. To calibrate this model, we use the low temperature transfer and output characteristic because the model doesn't really take into account the interface traps and thermal currents, which are present at high temperature. So as you can see, the model fits the experimental results really well, except for the substrate leakage at low VGS. The charge model of this model was also calibrated using the low temperature CV characteristics. As you can see, the CV characteristics start to show frequency dispersion at higher frequency around 5 megahertz due to the presence of series resistance from the quantum well and the source region. And in fact, we calibrated the model against the high frequency measurement from all the way to 10 gigahertz. With the well-calibrated model, the transfer characteristics of the quantum Watt TFET and the IV characteristics of the tunneling diode can be plotted in the red and black curve respectively. And as you can see, the intrinsic tunneling stiffness from the tunneling junction is about 34 millivolt per decade, meaning that the gate efficiency of this device is around 64%. So this value is unexpectedly low, and this is due to the unoptimized gate stack as well as the coupling between the gate capacitance and the tunneling junction capacitance. The gate efficiency was also extracted using simulation. It is a one-dimensional electrostatic simulation of the entire gate stack on the epitaxial structure. And the simulation was performed with self-consistent Schrodinger Poisson solver using the band and material parameters from previous literature. So the simulation was calibrated against the low frequency, low temperature CV characteristics, and you can see there's a very good fit between the simulation result and the experiments. So the extracted gate efficiency in the subthreshold regime is approximately 55%, giving 29 millivolt per decade of intrinsic tunneling stiffness. So the extracted gate efficiency from using simulation is very close to what we extracted using modeling. And in fact, the discrepancy between these two are from the are due to the neglected quantum capacitance in the model. So using the simulation and modeling, the intrinsic tunneling stiffness was extracted, which is around 30 millivolt per decade. And it is actually coming from the band edge stiffness, as I mentioned earlier, because if we take a look at the band diagrams of the device at different bias points, we can see that the valence band of the source is not yet aligned to the conduction band of the channel in the subthreshold regime. So this temperature-independent band-to-band tunneling current must come from the band-to-band tunneling in the from the states in the band gap. And in fact, the Urbach tail of the lightly doped InGaAs was measured to be around 30 millivolt per decade, which is consistent to what we extracted from the modeling and simulation. So the band-to-band tunneling actually happens in the theoretical forbidden regime and give rise to the finite stiffness of the intrinsic tunneling stiffness. So the next question is, how can we improve the gate efficiency of the quantum Watt TFET given it's so low? Because usually a MOSFET can achieve almost or even higher than 90%. So in this study, I want to investigate what these design parameters impact on the gate efficiency of the device. And here are the main design parameters, including the thicknesses of the gate dielectric, InGaAs layer, and the indium phosphide cap, as well as the doping concentration of both the channel and the source. In order to understand the relative importance of these parameters to the gate efficiency, there are 10 variations of the design by changing each of these parameters at a time. So by simulating all these 10 variations, we can have an idea about how these design parameters affect the gate efficiency. So here is the percentage change in maximum gate efficiency of the 10 variations, and these indicates the change of the variations of these columns. As you can see, the thicknesses of the gate oxide and the InGaAs layer, as well as the doping concentration of the source, have the most significant impact on gate efficiency. So if we want to improve the gate efficiency, we have to reduce all three values simultaneously. Taking into account the fabrication feasibility as well as some non-idealities that may caused by changing the values, such as series resistance, I came to the optimized set of parameters as shown here, which give rise to a 1.4x improvement of gate efficiency to almost 80%. With this improved gate efficiency, the projected substrate swing of the quantum Hall T-FET can be as low as 38 millivolts per decade at low temperature. And even with a moderate amount of interface traps density, approximately 5 e to the 12 per square centimeter per electron volt, the room temperature substrate swing can be 48 millivolts per decade, which is sufficiently low for low power digital application. So the next part, I'll focus on the non-logic applications of the quantum Hall T-FET. So here are the various circuit applications with using either MOSFET or diode. And due to the similarity between T-FET and both MOSFET and diodes, T-FET may be useful in any of these applications. So if we compare the devices, the T-FET have the advantage over MOSFET in power supply voltage, substrate swing, the presence of NDR, and strong nonlinearity. However, the T-FET also suffer from low current density and low GM, which are not preferred in digital and amplification application. Also, T-FET has asymmetric source drain design, which can be a problem for circuit designers to use T-FET. And if we compare the T-FET and the diodes, a T-FET provides an additional terminal, which is the gate, to have a gate control and input-output isolation. But T-FET has more complicated process, meaning more chip area, and the noise in T-FET is worse than the diodes because of the gate dielectric. So besides the logic applications, which requires high performance transistor characteristics and has not yet demonstrated using T-FET, ultra-low power RF applications may be suitable for quantum Hall T-FETs. So among all different RF circuits, RF detector is one of the most popular ones because of its wide application in security screening, in airports and medical diagnosis, millimeter wave navigation, and even the 5th generation telecommunication system. So the requirement for RF detector are high sensitivity, low noise, and small area and low cost. And the current device used on CMOS platform is the Schottky diodes, which is performing pretty good with very low cost. So as for sensitivity, the detector sensitivity comes from the nonlinear IV characteristics of the device, such as Schottky diodes and, of course, quantum Hall T-FETs. So the detector current sensitivity can be defined as the ratio between the DC current due to the incident RF power divided by the available RF power. And it can be written as in here. So this term takes into account the power reflected from the input due to the unmatched impedance. And then this term is the curvature of the IV characteristics, which represent the nonlinearity of the IV characteristics. So the detector current sensitivity can actually be calculated directly from the DC IV characteristic of the device. And if we remove the reflection and assuming a conjugated matched input, and also include the junction capacitance of the T-FET, we can write the matched projected impedance matched voltage sensitivity in this equation. So here is the detector current sensitivity measurement setup. The amplitude modulated signal with the power of PRF is fed into the gate terminal of the device, and then the resultant DC current was sensed from a drain and using a current amplifier and as well as a lock-in amplifier. As we can see that this device does not have any matching network, so that the input is not impedance matched. So on the left, I'm showing the measured unmatched current sensitivity at different biases. And current sensitivity increases with the increasing drain bias, and it peaks at the gate bias around threshold voltage. And and on the right, I'm showing the matched voltage sensitivity and the unmatched voltage sensitivity at different frequencies, and the achieved matched voltage sensitivity at relatively low bias, and at 2 gigahertz is above 100 kilovolts per watt. So what does that mean? If we compare this value to the state-of-the-art tunneling diode detector, it is around 100 kilovolts per watt, although this quantum multi-FET is not really optimized for this application. So that's why we observe very small band gap, very small bandwidth with quickly reducing voltage sensitivity with frequency. Another figure of merit people care even more is the noise equivalent power of the detector, which is the minimum power that can be detected with the signal to noise ratio equal to 1 within a 1 Hertz bandwidth. So by measuring the voltage noise power spectrum of the quantum multi-FET, we can calculate the NEP value with the carrier frequency of 1 gigahertz and the image frequency of 500 hertz to be around 3 picowatt per square root of hertz. And compared with the normal NEP achieved with Schottky diode on CMOS platform, it's around 3 to 6 picowatt per square root of hertz. So this device, although not optimized, is on par with the popular Schottky diodes using on CMOS platform. And I have to mention that this is the very first RF detection measurement on TFETs. And it was done in collaboration with Wenjun Lee and Professor Patrick Fay in Notre Dame. Another application I'm going to present is the TFET, quantum TFET based mixer. And it's also using the nonlinearity of the device, but again, this is going to be in the NDR region, which we are biasing this device with negative VDS. So here is an example circuit diagram of a quantum TFET based mixer, and we performed the circuit simulation using ADS and compared it with the CMOS double balanced mixer under these conditions. So because this is just a proof of concept, the frequency used for simulation are way lower than what we usually care about. So as a result, what's really catching my eye is this extremely low DC power consumption of the quantum TFET based mixer, because this device is only biased at 0.2 volts to bias it into the NDR region. And the DC current is only a microamp, and so the product of them gives us only microwatts of DC power consumption. Although the quantum TFET based mixer is not really optimized so that the other performance are not really comparable to the CMOS double balanced mixer, but I believe if the device is further optimized and that more complicated circuit design are included, it will become comparable to what we are using right now. So as a conclusion, we have successfully fabricated this quantum TFET structure with air bridge and self-aligned air bridge and self-aligned source recess. The achieved room temperature substrate swing is 87 millivolts per decade, and we observed good saturation at high VDS and the gate bias dependent NDR in the negative VDS region. So the temperature dependence measurement shows temperature independent substrate swing of 50 millivolts per decade below 140 Kelvin. So using modeling, we extracted the gate efficiency of approximately 64%, so that the intrinsic tunneling stiffness of the of the InGaAs on gallium arsenide and timonide heterojunction is around 34 millivolt per decade. And this is almost the same as what we extracted from the simulation. And then with the optimization of the design parameters, we can achieve 1.4x of improvement in gate efficiency to almost 80% from quantum simulation. And then the projected substrate swing at low temperature becomes 38 millivolt per decade, and the room temperature substrate swing, including a moderate amount of DIT, is 48 millivolt per decade, which is really promising for low power digital application. And then explore the circuit simulation, circuit application of the quantum T-FET, and the first one is the RF detection. The measured sensitivity, voltage sensitivity of the device, the projected voltage sensitivity of the device is over 100 kilovolt per watt at 2 gigahertz. And the device also exhibited very competitive NEP as low as 3 picowatt per square root hertz. Another application is the quantum T-FET based mixer, shown in this diagram. So the quantum T-FET based mixer shows very low DC power due to the low bias voltage and bias current, but the device shows relatively low conversion gain due to the unoptimized design of the device, and the input-output isolation is rather poor because there's a very strong coupling between the input and output due to the large CGD. So as for the suggestion for future work, I would suggest an experimental study on the design parameters as I presented earlier using simulation. And then I'll suggest for the experimental study of the quantum T-FET using alternative heterostructure, especially the InGaAs heterostructure with different tunneling compositions. And then I suggest an exploration of the scalability of quantum T-FETs, both in the intrinsic tunneling performance and the extrinsic parasitics. And lastly, I would suggest the experimental study of the quantum T-FET-based circuits using on-chip conductance and inductance and capacitance to truly review what the device should behave using the non-ideal components. So I would like to thank my advisors, Professor Judy Hoyt and Professor Dimitri Antoniadis, and they gave me valuable suggestion and guidance for years of study, and I wouldn't be able to stand here without him. And then I would like to thank my family and friends, especially my girlfriend, Zoe. Where is she? And I would like to thank my collaborator who helped me a lot for all these study, and also valuable discussions with other students and professors from both MIT and Berkeley. And I would like to acknowledge the funding from the Center of Energy Efficient Electronics. And I would like to thank all the MTL staffs who helped me a lot overcoming all these fabrication issues. So that'll be all of my presentation. Thank you very much, and I'm open to any question you may have.
Do we have any questions from the audience? I have one question. In the 30 millivolt per decade intrinsic turn-on, which is based on the band tailing, the assumption is that the tunneling factor, the transmission coefficient, is constant, right, through the variation of VG. What would happen if the distance is modulated at the same time as the potential is bending?
Sure. So, yes, this is actually a combination of tunneling transmission coefficient and the density of states. But if you take a look at the band diagram here, the tunneling distance is not varying much. So it's basically the thickness of the InGaAs channel thickness, especially at the beginning of the turn on of the device. So the transmission change of transmission coefficient wouldn't be too much, but in fact, if we try to separate them, it would require a lot more simulation and modeling work to do.
Okay, so basically the turn on, at the turn on, what you're saying from this simulation, which is based on next nano?
Yeah.
There is no modulation of the distance.
Yeah, there is no modulation at distance at the beginning, but in the later, when the bands start to overlap with each other, and the modulation will become, because at the beginning it tunnels into the farther place when the band is not bent so much, and then it will tunnel into a closer location when the bands are bent with high gate bias.
Okay.
So I have another question. So you basically have shown that in low temperature you have 50 millivolts per decade slope, right?
Yeah.
And that's, can you claim that that's better than MOSFET in terms of the slope? Because the slope for MOSFET is essentially KT over Q times log 10, which is also temperature dependent.
Right. So
what's the comparison?
I think the message I'm trying to give out is that band-to-band tunneling doesn't have temperature dependence. So if we can optimize the device, optimize the density of interface traps, and get rid of, not really get rid of, but suppress the thermal current low enough, we can achieve somewhere close to 50 millivolt per decade, because that's independent of temperature. And at even higher temperature, which is happening on in most of the scenario, like CPU, and the substrate swing of MOSFET get deteriorate, but this remains the same.
So can I say that your TFET, even with this 80 millivolt per decade room temperature, it's going to be better in high temperature operations in the real world?
It could be. I didn't do the measurement, but assuming
MOSFET will be worse.
Yeah, MOSFET will be much worse. But if the device is dominated by band-to-band tunneling current, which is very much the case in my device, it will eventually behave better than the MOSFET at higher temperature.
Any other questions? Okay. Well, if we don't have any other questions, then let me close the public part of the thesis defense. Once again, let's thank Tao.